keep adding sort of layers of the onion to this function. But the innermost layer is what would you do first if you threw a number at this thing? And the first thing you would do, if this was 2, is you would hit right there and you raise it to the third power. Yeah, kind of. The order of operations is more if I have 2 plus 3 times 4. Order of operations means I multiply these guys before I add the 2 and 3. I don't say this is 20. I don't say 2 plus 3 is 5, multiplied by 4, I get 20. Order of operations means 2 times 4 is 12, plus 2 is 14. That's what order of operations is. But on this, it's more just the order you would actually do it. What I'm saying is, I'm just trying to say this because sometimes it's not obvious with the chain rule. What is the innermost function? And what is it? And so to me, an easy way to think of it is what's the first thing you're going to do? You're just trying to just plot out evaluate this. The first thing you're going to do is you're going to say, okay, this is 2, so that's 8. What's the next thing you're going to do? Cosine. Yeah, so that's the next layer. So I'm going to take the cosine of 8. And I'm going to get whatever that is, whatever units we might happen to be in. I don't know if it's 8 radians or 8 degrees or whatever. So then we get a value for this whole thing. And then we're going to raise 2 to that power. So that's the next layer. And then, okay, now we're going to take the sine of that whole thing. So that's the outermost layer. So the outermost layer is this, sine. Next layer is the 2 to the whatever. Third layer, cosine of the innermost layer is the x to the third. And so the way the chain rule works, just get back to a simple example for these guys, is you take the derivative of the outsidemost function. And so the outsidemost function here is the cosine. Okay? So I'm going to differentiate that. I'm just going to treat this as sort of a black box. So as we already know, cosine of x is negative sine. So I'm going to differentiate the outside one. So I get negative sine. I keep my, whatever my term here is. And then what I do is I multiply it by the derivative of the inside one. This is the chain rule. So the inside one here is this guy. So the derivative of that is 3x squared. So I'm going to multiply this whole thing by 3x squared. And so that is the derivative of this guy equals that. Okay? You take the first take the derivative of the outermost layer, and then you multiply it by the derivative, and just evaluate keeping this part the same. X to the third, we don't change it. We're just differentiating the outermost function. We don't care what the term of that function is. And then we multiply it by the derivative of the inner function. And so if we were to keep going with my, what did I have? I had, so I had cosine, I don't know if I'm writing my funky equation that I did for the moment. And I had that raised to 2, and I took the sine of this whole thing. So if I want to differentiate that, I've got 4 layers deep. I've got this function, I've got the cosine, I've got raising 2 to that, and I've got the sine. So what I'm going to do is I'm going to take outermost layer, which is the sine. The sine is the outermost layer of this particular onion. So I'm going to take the derivative of that, so that's just cosine of x. So I say cosine, and I just keep all this stuff. 2 cosine x to the third. Okay, now I have to multiply by the derivative of the inner layer. This is the next layer in. This is 2 to the cosine, blah, blah, blah. And so we said that right here is 2 raised to something. So we're going to take the natural log of 2. So we have times ln 2. We'll multiply it again by this whole guy. 2 the cosine x cubed. And now we have to multiply it by, so now we've gotten into this layer. Now we have to multiply it by the derivative of that. So it's just we have 4, the negative sine of x cubed, multiplied by, now I've got innermost layer, 3x squared. So this is the derivative of that. And so that's the chain rule. are. So just a preview of events to come. I'm probably going to get into talking about dot products and cross products next lecture. And I'm going to try again to explain in kind of a, my goal here is to tie this stuff into real world things, hence why I'm dropping a pinball from an elevator. So that's kind of what my teaching style, I guess, is I don't want to have it all be purely abstract. It's like Carl was doing, settle down, settle down, settle down. So what Carl was doing was all correct. And the thing is, Carl knows this material way better than I am. Right? He's been preparing this class for years, apparently. I'm serious. He's got tons of enthusiasm. He's a very smart guy. And he was teaching like an MIT grad class too. And they were wrong. Okay?
You wouldn't relate it to anything.
Yeah. So, like, if you go to a research university, and you're not at one, but if you go to a high-level research university, you'll have some postdoc who's writing gibberish, might as well be, on the board, and they will never turn around. Practically ever. And they'll just keep going, keep going, keep going, keep going, and they will literally never turn this place to class. And they will never ask you, does anyone understand that, does anyone have any questions? And that's one of the advantages of not being at a high-level research university. This school is teaching oriented. This is all about teaching. That's what that's for. We're here for, that's what you guys are here for. And so anyway, what Carl was doing, I mean, I'm sure he did turn around and face the class, but the level he was teaching it at was, I said, I looked at it, and I kind of blanched, and like, this is a grad class. The way he's teaching this is a grad class. So don't beat yourself up about maybe not entirely grasping it, the way he was doing it. And so I'm not going to be able to cover as much material as he did, or perhaps as much sophisticated problems, but hopefully what I do cover you will follow. That's what I'm hoping for, at any rate. So I'll see some of